In this video, we will use the MATLAB Deep Network Designer to build a neural network. In the previous video, we used lines of code to program in a neural network structure. We will use the same network structure in this video, but by using the MATLAB Deep Network Designer, it allows us to clearly visualize what we are doing and shows us what options we need for each layer. We will discuss each layer as we build it. Open MATLAB and click on the Apps tab. In the list of apps, you should see Deep Network Designer. Note that you may have to install the Deep Learning Toolbox for this to appear. Open this app. You will have the choice of either opening a blank network, a network from the workspace, or a pre-trained network. Select Blank Network. You should now see the Deep Network Designer page. You can build your network in the Designer tab. The first thing we need to do is to input an image. Drag the image input layer icon from the layer library on the left into your workspace. On the right of the screen, the properties for this layer are shown. Our input image is 28 by 28 by 1, so we need to change the input size from the default 227 by 227 by 3 to this value. The convolution layer is essentially a set of filters that we pass over the image. We do not decide on what these filters should be. The neural network will train itself towards whatever filters it needs. As an example, consider a neural network trained to recognize cyclists. We will assume all cyclists wear yellow jerseys. When the network is trained, we may find one filter highlights the color yellow, whereas another filter may highlight edges of objects. This will highlight the circular shapes of the wheels. If you look back at session 6 on filters, the filters were 3 by 3 matrices, and we moved them over the image a step at a time to get a filtered image. This reduced the image size, but we did have the option of 0 padding, to allow us to have the filtered image the same size as the original image. The convolution layer is doing exactly the same process on the input layer, although it is running several filters over the image to produce several outputted filtered images. Add a convolution 2D layer to your network. Connect this to the input layer by clicking on the small circle on the icon's perimeter and dragging the connecting arrow between the blocks you want to connect together. If we look at the original MATLAB code, we can see this layer had parameters of 3, 8, and padding set to be the same. We will therefore set this layer to these values on the Deep Network Designer. Click on the question mark at the top of the Properties box, and a MATLAB help page will open describing what each of these parameters are. We can see from the description we have set a filter of size 3 pixels by 3 pixels, which is similar to what we did in session 6 on filters, and have chosen to have 8 filters for this layer. Setting padding to be the same means our outputted images will be the same size as our input image. A normalization layer scales all of the values. This stops numbers from becoming too large or too small as the training repeats. This normalizing of values also helps to speed up the training process, as values are kept within an acceptable range. The ReLU layer is our nonlinear function, which is used to convert the sum of all the inputs into an output. In our original description of how neural networks work, we used a hard limiter in which the output was 0 or 1. In the case of this ReLU function, our output is 0 for values less than 0 and x for values greater than 0. This can be seen from the small graphic representing this block. There are lots of options to choose from for this layer. For example, the tanh or clipped ReLU layers are similar functions to our hard limiter, although with gentler transitions. Pooling is a way to reduce the size of the network. This layer will analyze several pixels at a time, but reduce this group of pixels to a single pixel. The operation may average all the values, or it can consider only the largest value in the group. In our case, we will take the maximum value of this set of pixels using the max pooling command. As with filters, the size of this pooling and the step size over which this process is scanned over the image is defined in the parameters. Not only does this operation reduce the image, and therefore training time, it also helps to train the network towards a more generalized solution. For example, if we are looking for a feature at a particular location in the image, the max pooling layer allows us to look for that feature within that group of pixels, rather than at one very specific location within the image. After adding these three layers and connecting these together, your network should look like this. Note that of these new three layers, it is only the max pooling one that needs its parameters changing to the values of the MATLAB program. If you wish, you can click on the Auto Arrange button to tidy up your positioning of your layers on the screen. Layers in a network can be repeated, with these new layers acting on the previous outputted images from the last layer. This allows for more generalized features to be extracted from the original image. Our MATLAB program repeated the convolution, normalization, and ReLU another 2 times, and the max pooling layer 1 more time, as can be seen from the code, albeit with slightly different values. We therefore need to add these new layers to our existing network. Our network should now look like this. Note that I have rearranged the blocks slightly to make it easier to view. The image flow is still in the direction of the arrows, regardless of how it is arranged on the screen. The fully connected layer is used to extract the features identified from the convolution layer, i.e. filter layer. The output from this layer will be a set of values that shows us how likely it is that the original image is represented by each one of our digits. The softmax layer normalizes the values from the fully connected layer. This gives us the probability for each digit that it is represented in the original image. The classification layer chooses the highest probability from the softmax layer and outputs this as our answer to the digit recognition problem. Your final layers of your network should now look like this. One point worth mentioning here, and discussed later, is that dropout layers are also commonly used. This randomly omits data from the analysis to help give a more generalized solution. More on this later. Now that the network architecture is set up, we need to select the training data. On the Data tab, select Import Data and you should see a window similar to this. We need to tell the app where the data can be found. This example data can be found in the MATLAB directory. Select Browse and follow this link to locate the data. There are options for when you are loading data. For example, we can alter it in terms of rotation, translation, etc. We will keep the default values for now. We need to create our validation data, so we will split this data into 75% for training and 25% for validation. We also need to make sure our images are the correct size. Fortunately, this app will check this automatically for us and resize them if needed. Your import data window should look something like this. Once imported, you will be able to view the data. The final tab is for training. You have the opportunity to set the training options here. So as to keep this network the same as our previous example, we will set max epochs to 4 and validation frequency to 30, although you can play around with these if you wish, to see if you can improve on the performance. Once these have been set, you can train the network. During training, you will get a plot similar to this. Ideally, you want a high accuracy, low loss, and the validation to be similar to the training. The time the training takes will depend on the complexity of your network, which is fairly simple in this case, and the processing speed of your computer. In this case, the computer has a dedicated graphics processing unit, or GPU, as indicated on the right of the image. This speeds up the training. The time to completion for this was 5 seconds, and the results report back a validation accuracy of over 99%. Note that complex networks can take days to train. Now that we have our network, we will want to use it. You can either export the network, or you can export the MATLAB code needed to generate the network, as shown here. You are now in the position of loading in your own images and get the network to read them. There is one final point to consider before we leave this section. If you remember back to our original discussion of neural networks, we saw how the weights and bias values were set in order to give the required output. We can look at the values within our new network. Once the network is run and shown in the workspace, click on Net to show its values. There are lots of levels and lots of values within this. Here I have selected the layers, then clicked on the second convolution layer, which is our 16 filters in layer number 6, and then selected the weights for these filters. The right side image shows you a selection of these weights or values within these filters. Note that we specified each filter to be 3 by 3, which is the 3 by 3 groups of numbers you can see here. We chose 16 filters for this layer, and this layer has 8 filtered images coming from the previous filter. So we will have a total of 16 times 8, namely 126, of these 9-element filters in this layer. As you can see, this network, despite still being relatively simple, is much more complex than the basic neural networks discussed at the start of today's session. In the final video of today, we'll see a few final considerations when building and training your network.